Welcome everyone to another CP Tap call. This is call number 135. I'm pleased to introduce today's speaker, Seth, a seasoned leader in over 2 decades of experience in electronic trading. He has a strong background in sales trading, technology, and consulting, and he's the inventor of multiple patents in order processing technologies like since 2010. Since Seth has held a key leadership role at Morgan Stanley Japan and Nomura, where he built and led electronics and quantitative trading businesses across Asia. He now serves as a CEO of Liquid Market Solutions, where he drives product vision and innovation. And today's talk is about the Ubernic and basically the aspect of precision time in it. So with no further ado, Seth, the floor is yours.
Okay, thanks. Hello, everybody. It's been a while since I presented. So the last time I presented was pretty much at the beginning of our Ubernic project, and talked about what it was going to be. And today I have the pleasure of being able to present what it's actually become. So we did a lot of engineering over the last 2 years, spent about 1 year in a proof of concept phase with a bunch of firms around the world. And on April 18th, so just about 2 months ago, we released the first full production version of the software and hardware logic. And today I'm pleased to be able to share you, with a particular focus on precision time, how all of these different parts of the product come together. So I'm going to not walk through a gigantic deck. I'm going to focus a bit on a two-pager that we have, and then I'll cover a few slides from the deck. But what I'm most pleased to be able to do is actually show you Ubernic running live. Unfortunately, I'm not sitting in the office, so I can't point the camera at it, but the reality is this is all electronic anyway. So even if I could point the camera at the platform, you'd see a really nice piece of painted plywood, a motherboard, a couple of FPGA boards, and some flashing LEDs and blue liquid coolant, keeping the thing cool but quiet. So it'll be some terminal windows, and we'll go from there. So Ahmad, if you could let me share my screen, and
You should
then
be able to, yeah.
okay, cool, thank you. And then, so I'm going to there'll be an infinite loop here for a moment, and then we'll go through this. Don't look at that yet. So just to get started, let's first start with a brief two-pager. So an awful lot of what we talk about with precision time focuses purely on precision time, right? We go to ITSF, we go to ISPCS, we do other discussions, other talks, and we're just focused on, this is what we can do to get more accurate time. Or, Ahmad gets a soldering iron, solders some wires, and shows people, look, PTM is working. We get a scope and we connect that and we show PPS signals. But we don't really talk about how all of this comes together in an end user product, how it's really used in the end user world. And that's what I'm going to try to talk about today. So we set out to build a product called Ubernic with the little umlauts. The Germans always ask me about that. But it's an accurate meaning, because we set out to build a product and we use the word Uber to mean over, beyond, better. And in this case, we believe, and I think most of our clients believe, that's what we've accomplished. So Ubernic is an FPGA general purpose Ethernet NIC and FPGA-based network stack. And so the primary goal in any network stack is network I/O. And of course, with us, that's the fundamental basis of the product. And what we've built is literally the lowest latency, highest capacity, most consistent NIC in the world. And it's easy to say that, but it's not just marketing speak here. We've actually been benchmarked by independent third parties. And in fact, according to them, we are the attributes that I just described. But to be better and to provide a more value, particularly value for money, in an expensive exchange-focused co-location environment, we have to have more features within a single product. And so that's where some of our other capabilities come in particular precision time. And so while low latency, while ultra high performance network IO is critically important for us, precision time is just about the same critical importance because both of those things come together to build the overall capabilities of the product. So from the standpoint of a NIC, if we receive data from an inbound transceiver and we take a timestamp at the point immediately external as the fiber is connected to the QSFP in our case. And then we take a timestamp on the transmit side. We're capturing the total latency for the particular frame and the bit position immediately following the start of frame delimiter to traverse Ubernic itself, traverse the PCIe bus, be delivered to a memory address, picked up by what we call the tick-to-trade application, and then immediately transmitted, and of course, back across the PCIe bus, across Ubernic, network headers being built, and the data leaving the QSFP. So we call that network IO, the total network IO. And for Ubernic, the minimum latency across 64-byte payloads, and this is 5 million test frames. So we don't do 100 frames and say, look at our best result. We actually like to stress test this and test it the way people in the real world would use it. So our minimum latency for, again, 64-byte payload, which is a typical financial services order message or market data message, is 784 nanoseconds. But note, the 99th percentile latency is 910 nanoseconds. That's a pretty tight spread across 5 million frames. Our standard deviation, 99th percentile, is 20.45 nanoseconds. Again, extraordinarily consistent. And another way of looking at consistency, oops, sorry, I wanted to just move this little Zoom header, okay, is if we look at, again, 64-byte payloads, but at a particular throughput rate, 2.5 gigabits per second, which is a typical burst rate on the New York Stock Exchange. And so at 2.5 gigabits per second, and this is a single throughput rate, so this is now 50,000 frames, we processed 99.8% of the messages in less than 949 nanoseconds. In fact, it's a 108 nanosecond window between 841 and 949 nanoseconds. So 99.8% of 50,000 frames means the tail is 100 frames. And so that's extraordinary consistency and also very, very, very low latency. So again, from the standpoint of network IO, that's what we've been able to build. But by itself, while that's obviously very interesting and intriguing for people, that's not everything people would want. And so there are other features, again, precision time, and then we can combine those two things to create other capabilities that people would like. And so just a couple of more blurbs about Ubernic, and you can see the photo of one of the flavors of Ubernic we have. There are a couple of different physical models, some with Altera FPGA chips, some with AMD FPGA chips, some with a single QSFP-DD, as you can see in the picture here, others with two QSFP-DDs. But the key thing is that physically, they are all single PCIe slot. So we recognize that servers are expensive, and the number of 16-lane slots in servers are, a portion of the overall PCIe slots. And the days where you would have an FPGA product and you would have a heatsink that was so thick, it would overlap onto the second PCI slot, and ultimately you have an empty slot because there's no physical space for it. In 2025, we can't justify wasting money that way. Again, servers are expensive, CPUs are expensive, memory is expensive. All of this goes inside of a rack in very expensive data centers. Electricity is expensive. Cooling, of course, which uses electricity, is expensive. And overall value add is more and more important, even in financial services where people theoretically have unlimited money, so to speak, to throw at a problem. Well, unlimited money is, not so unlimited at the end of the day when, you're spending tens of millions of dollars on equipment to purchase it and even more money to actually maintain it on an annual basis. So efficiency of space utilization and energy utilization is very, very important. And while this isn't in the deck or in this two-pager that I'm showing, let's just talk about energy for a minute. So I think we're all aware of AI and the soaring electricity needs associated with data centers in general. So let's put some numbers to that. From 2022 to 2024, energy usage in data centers grew by 73%. And energy usage is forecast to grow another 128% over the next 5 years. And as we know, people are scrambling to find energy sources, right? 3 Mile Island in the US, after years of being idle for the nuclear accident that occurred back during Jimmy Carter's presidency, has been brought back to life. It's not going to be the last time we see things like that happening. So when we stop and think about energy utilization, let's look at a typical network interface card that's used in financial services, what's called the X2522, which is a product of the former SolarFlare that was bought by Xilinx, that of course is now owned by AMD. The 2522 has two physical interfaces, and the board as a whole consumes a little bit more than 14 watts. So if we look at the board and we say two interfaces, 14 watts, okay, 7 watts per interface. We're an FPGA. The board itself and the chip, we consume about 51 watts. Well, that's significantly more, of course, than the 2522. However, because of the transceivers, because of the cage, which is a QSFP-DD, for 110 or 25G, we can actually get 8 fiber pairs. So if we look at watts per fiber pair, we're actually 6.4. So we're more efficient from an energy utilization standpoint. We're a single PCIe slot. The 2522 is a single PCIe slot. So once again, we talk about the efficiency that we're able to get out of that single slot, including energy efficiency, which is a bit counterintuitive because, of course, most people think correctly that an FPGA will use more energy, and it will. But if we make efficient use of that, if we have an efficient design, we can convert the inefficiency into something that's very efficient. So then a couple of other key points about Ubernexos, I think is not going to be a surprise given what I'm saying. We offer significantly higher throughput rates than traditional software network stack solutions. So again, comparing ourselves to other products, in this case, the AMD Alveo 3522, which is an FPGA-based NIC, but it implements software network stack. That has 2 SFP DDs, so that means the capability of 4 fibers. And for 10G, that would theoretically mean the throughput rate is 40 gigabits per second. But the network stack is actually reasonably inefficient. Latency starts to climb at about 1.5, 1.6 gigabits per second. Around 2.4, 2.5 gigabits per second, the latency is now 28 to 30 microseconds, and it starts dropping frames. Now, in a normal data center world, okay, a frame is dropped, there's a resend, it's a bit of network inefficiency, but beyond the inefficiency, what's the problem? In financial services, actually, that's a huge issue. If frames are being dropped, that means that messages are not being delivered. And whether it's TCP or UDP, no matter how you look at it, it's a problem. At the very least, it's an economic problem. You're not able to make a trade that you might have otherwise made, which means you're not achieving a profit that you could have achieved, or you're not avoiding a loss that you could have avoided. That's bad enough. But the other problem is that from a regulatory standpoint, most firms of particular types, brokers, certain types of hedge funds, exchanges, are actually required to maintain data and to demonstrate that they made correct decisions with the data that they received. Actually, I should phrase that a different way, with the data that was transmitted to them. And if you don't receive a message because it was dropped somewhere in your system because your system couldn't handle the throughput or a burst throughput in a very short-term basis, the regulator doesn't really care about that. That's your problem. So if you fail to maintain total data records, that's an issue, especially in Western Europe. If you're not able to demonstrate that you made a correct trading decision, there are many different trading venues. Securities, the same security can trade on many different venues at the exact same moment. On one venue, there might have been a slightly better price than another venue. So if you send an order to venue B, but the best price was on venue A, regulator's going to come in and say, why did you do this? According to our records, there was a better price here. Why did your system make this decision? And if the system made the decision because it was missing data, that's an issue. And the regulator will ding that particular firm and will fine them. And then with a fine, it's not just a monetary impact, it's a brand reputational issue. And so being able to support line rate throughput is critical. And so we come back to the SolarFlare 3522 with its theoretical 40 gigabits per second capability. In reality, its actual capability before it starts to break down is only a little bit more than 4.8 gigabits per second. So only a little beyond 10% of the theoretical capability. Whereas Ubernic can support full line rate, 10G, 25G, of course, 1G, all day long across all 8 fibers concurrently. And so we deliver a vastly different technology outcome. And of course, as you've heard me emphasizing, there's a business outcome. If CapEx can be reduced, that means companies that are buying equipment, deploying equipment, can be more efficient in their overall capital expenditures. And of course, if OpEx can be reduced, then that's an even bigger savings, right? CapEx is a one-time event, OpEx is a multi-year event. So being able to help firms save OpEx is very important. Quick little comment about LMS. I think there are a number of folks on the phone who have known us from either their current roles or their previous roles. So, our partners include, some very well-known firms, and we work closely with all these folks, Intel, Altera, AMD. Bitware, of course, is the exclusive builder of all the FPGA boards that we use. Red Hat, Jabil Dell, Blackcore. The icon on the bottom right is vCity. That's a Chinese mainland reseller. And of course, what we're talking about today is Precision Time, and so CERN and White Rabbit. And one of the things I'll show in a moment is White Rabbit actually running live. So that's sort of a business summary. If you're a business manager and you're wondering why you should care about Ubernic and Network IO, that's why. And then from a technical standpoint, something for the technical side to turn the other page and look at. We have a diagram of the same Ubernic that there was a photo on the front side. Again, this is an FPGA-based platform, so that means FPGA-based network stack. So this is complete offload. It's not a TCP offload engine. It's not partial offload. This is complete offload. And with that, that creates lots of capabilities to do some of the things that I've already mentioned and that I'll show in more detail in a couple of minutes. One particular thing, it's a bit of a technical detail, but it's something that is important in terms of the overall performance and something that's very, very different from software network stack solutions. Because we are able to operate essentially at line rate, when we're receiving messages, we have to deliver those messages across the PCI bus to the host side. Now, of course, we're running the network stack and the FPGA chip. So unlike a software network stack where, for example, if we have a 64-byte UDP payload inside of the Ethernet frame with the FCS, that's 110 bytes. And so it's 110 bytes that goes across the PCI bus. And of course, any PCI bus transit is assigned flow control credits to manage that. As we all know, flow control credits are a finite resource. There's separate metadata for PCIe, and of course, that has its own FCC assignment. So anything that we can do to reduce the size of data going across the PCIe bus has a direct relationship with reducing the flow control credit usage. So in our world, it's not a 110 byte message that goes or frame that goes across the PCI bus. It's the payload. In the case of UDP, a payload plus 8 bytes of metadata. Metadata being the IP address that sent the message and the port that sent the message, so that the consuming application can identify exactly where this message came from. So that means 72 bytes versus 110. So pretty significant reduction in size, with obviously a pretty significant reduction in flow control credit usage. And so the data goes across the PCI bus. But because it's a hardware network stack, now that data doesn't need to be processed by a network stack or, from a financial services standpoint, market data protocol handling. It's already processed. It's done, ready to be consumed by the target application itself. So we're delivering the data to an address space. The application can pick it up directly and can work with it directly. All of these individual capabilities combine to be able to move the data through the system at very, very, very high rates, which is why we're able to achieve the throughput rates that we can achieve. And then another innovation in all of this is what we call wire order delivery. So software network stacks are simply not able to process the data at, as I said earlier, anywhere close to line rate, not even half of line rate. So that data has to go somewhere, and it's going to go into a receive buffer. But receive buffers are often limited in size, so there will be multiple receive buffers for individual sessions. And what that runs the risk of is that messages, because they're being fed into different buffers, are then actually processed and ultimately consumed by an application out of order. And so some vendors have spent a pretty significant amount of time creating software applications that can look at this data and try to reassemble it across these multiple queues to put it back into the order that it was in as it came across the fiber. We don't ever have that problem in LMS because we operate a single receive queue per session, period. So data is automatically, by virtue of a single receive buffer, receive queue, is already automatically in wire order delivery. And so it's a simple little concept. In software, that would be, again, extraordinarily difficult, if not impossible, to actually implement. But because of the overall architecture of Ubernic, it's actually allowed us to create that capability. Ubernic is also a programmable SmartNIC. So we allow clients, through a series of defined interfaces, to create their own hardware logic, put it in the FPGA, and then interact with our logic directly. So clients don't have to worry about trying to build their own network stack or buy IP blocks and integrate them together. They don't have to worry about trying to build precision time, whether it's PTP in hardware or White Rabbit. They don't have to worry about building timestamping and packet capture capabilities. We provide all of that. They can simply focus on the core application that they're trying to build. And then precision time. So, again, when we first talked about Ubernic a year and a half ago, it was about what it was going to be. And today it is. So today we have implemented White Rabbit. Next week is the annual White Rabbit conference in CERN. We are founding members of the White Rabbit collaboration. We will be there, and we will be taking our demo platform and demoing Ubernic with White Rabbit live at the event. So what is White Rabbit actually capable of? So the White Rabbit implementation that we have, we're able to achieve 99th percentile synchronization to a White Rabbit switch of plus or minus 2 picoseconds. And I'll actually show you it running live in just a moment. We also implement PTM, so updating the host real-time clock across the PCIe bus using precision time measurement. You'll also see that ticking away live. And then something that is certainly very dear to, certainly Ahmad's heart. I'm not sure if Julian's on the call, but Ahmad, I'm sure you'd agree, is also dear to Julian's
Yeah.
heart, is TGPIO. That is running. I don't really have, again, it's all remote right now, so you'll be able to see it ticking in a terminal window. I don't really have the scope connected to be able to show that, so you'll just have to look at the terminal and believe it. And so with those three pieces, we have a holistic precision time capability. So with White Rabbit, we synchronize to the White Rabbit switch. Obviously, the White Rabbit switch, little tongue-tied there, would be synchronizing to a Grandmaster, but obviously connected to GNSS. Sorry, I need to turn my light on here. And then with PTM, we're obviously updating the host real-time clock. And with time-aware GPIO, we're bringing a PPS signal back from the CPU into Ubernic. And because time from the host perspective is driven by PTM from Ubernic, then what we do, which I can't really show you here because I don't have the scope set up in a way that we can see it, is we compare the PPS, the internal PPS in Ubernic, to the PPS coming from the CPU, and we can see what that skew is, and then we can further adjust. Now, one important thing to keep in mind about PTM is it is driven by the crystal clock behind the always running timer. There is no multiplication of it. So what we expect is a skew that is equal to 2 times that frequency. The CPU that's being used here is the Xeon 5th gen W72595X. So it's a workstation CPU, the top of the line CPU for the workstation series from Xeon 5. We can overclock that. So we can get some really good low latency performance out of it, but that clock is running at 24 megahertz. So we would expect a 48 nanosecond skew between the PPS from the CPU and Ubernic. Anything other than 48 nanoseconds, anything less than, anything greater than, we then adjust our time that we're communicating with PTM to account for that delta to then make the time more precise. And so again, holistic solution. Now for TGPIO, it's great in principle. It's not as accurate as it could theoretically be, but given what the industry has available today, it's as good as you're going to get. The challenge is that it's really, to say that it's not widely supported on motherboards doesn't do justice to how not widely it's supported. And I'm sure Ahmed is like nodding his head up and down right now at that one. So there are very few motherboards that actually support this. If we look at the data center world, there are 2 servers from Jabil. Jabil's a big white label contract manufacturer that actually started coming to market with its own branded servers a couple of years ago. So we worked with them and with a helping nudge sledgehammer from Ahmad. They got the same message from Ahmad and Julian that they got from us. And so Jabil has implemented TGPIO on 2 of their 3 servers. So they have 2 different servers for 2 different servers for 4th and 5th gen Xeons. They have another server for the 6th gen Xeons. They have yet another server for AMD, but that doesn't count because they don't do TGPIO. So that's the only data center server that actually supports TGPIO. And Jabil has the plugs implemented for, these are both dual socket CPU servers. And there are 4 TGPIO plugs, 2 for each of the CPUs. So it's exactly what you would want, which is not a surprise because they literally looked at us and then looked at Ahmad and Julian and said, what should we do? And we said, this is what you should do. And I know Ahmad said, this is what you should do. And they went and did exactly what we all collectively said they should do. So that's cool. The other is ASRock. So ASRock has taken a couple of motherboards, obviously a workstation motherboard, a server motherboard, and they've also implemented the plugs on that. The problem with ASRock is they just don't have a lot of penetration of the data center space. So far, Dell, HP, Lenovo, and other organizations have been blissfully sort of burying their head in the sand on this overall topic. So that's unfortunate because it has a lot to offer. But people have to see it being used to get what's important about it. Another point around Ubernic, just before we start looking at real data, is the actual oscillator that is implemented. So at the moment, we're in what we call sort of a revision 0 and revision 1 of the different boards that have not the greatest oscillators in the world. We're now working with Bitware on revision 2. That should be available in October, November. That is going to implement a much different time time circuitry, sorry, and a much higher quality oscillator. So we're going to move to an oven-controlled oscillator. There's already a prototype of that on a different Bitware board that we're working with, and that board, while not quite having the network I/O capabilities that we would like, it has a QSFP56, not DD. It actually has two M2 sockets on the FPGA board, so we can plug in NVMe sticks right there at the network edge. So we can get 2 8 TB sticks, 16 TB of data storage right there at the network edge. And that board is the prototype for the revised time circuitry and oscillator. And we at Bitware are collectively working on bringing that board up. And then that circuitry, once we've proven it, is going to go into the revision 2 of the core Ubernic product. I'm not going to read this other stuff. I'll ask Ahmad to make it available or distribute it to everybody so you can look at it as you want. I'm going to minimize my screen at the moment and talk a lot less about network I/O latency and focus a bit more on what we're all here to talk about, which is precision time. So I'll first go through this slide, and then I'll show the terminal windows ticking away with various things, and you can see things operating live. For those of you who were either involved directly or sort of on the periphery of what we did in the fall at ISPCS, ITSF, and with the CERN people in Japan, we had some invitation-only events to show people with live demos of White Rabbit, and that was where we first actually publicly unveiled our White Rabbit. So it's about 8-9 months old at this point. And so this slide summarizes the overall precision time capabilities of Ubernic. So first, we do support Linux PTP. We recognize that obviously a hardware implementation of PTP is going to be better than a software implementation of PTP, but for a variety of reasons, some people just still want software-based PTP, so we support that. We have a hardware implementation of PTP that we call Uber PTP. Sorry, we're not the most creative with naming, but at least it's clear. And so that also highlights another capability of Ubernic. Even though it's a QSFP, we can actually set the link speeds of the individual transceivers and therefore individual fibers. So we can run some fibers at 10G, some fibers at 25G, and still operate one fiber at 1G for the PTP and particularly White Rabbit time sync networks. So again, this is just an overall visualization of the different capabilities. So we've got what we call infrastructure time sync. So the GNSS receiver to a switch coming in, could be Linux PTP, could be Uber PTP, could be White Rabbit. Obviously, that's coming into the FPGA for the latter two. For Linux PTP, it's just flowing across the PCI bus with PTP4L, and we know how all that works. And then we use PTM, and where we're managing the time, and then we're of course pushing those time values across the PCI bus to update the host real-time clock. And then of course with TGPIO PPS, we're bringing the pulse per second signals back into Ubernic. Normally, this PPS inbound isn't really connected. If you're using White Rabbit, we only use that plug as an outbound PPS when we're doing the initial calibration, but we're trying to represent 3 different scenarios in this diagram. So, the CERN folks are like, no, that's not correct for White Rabbit. And they're absolutely correct, but we're trying to represent 3 different things. So I'm emphasizing if it's White Rabbit, this connection is not there. So we bring the pulse per second in from TGPIO. Of course, we have our own internal pulse per second. And as I mentioned earlier, that's where we're comparing things. So keep this diagram in mind as I describe next what's going on. Okay, so we got a couple of different windows here on my desktop. Let's focus first, bottom left. Okay, so this is White Rabbit. Some of you may have seen this before. This is an application that comes from CERN that you can use to monitor what's happening with White Rabbit. There are a lot of key numbers here, but the most important number is offset from master. And this shows just how precise, or theoretically not precise, the alignment is between the White Rabbit clock in Ubernic and the White Rabbit clock and the White Rabbit switch. And so as you can see, at least for this brief moment in time, that offset is 0.000, so third decimal nanoseconds. So the third decimal of a nanosecond is, in fact, a picosecond. And so what you can see, apart from one brief minus 1 or now 1, this is 0. So as I said, 99th percentile, our time resolution is plus or minus 2 picoseconds. And you can see it right here. Now, there are obviously some people who will be disbelieving of this and who will say, oh, you're controlling it, you're manipulating it. Well, this is one of the reasons that we actually show things in a scope. So then we have a coax cable from Ubernic. We have a coax cable from the White Rabbit switch connected to a scope. People can see it for themselves. Now, obviously, in the scope, it's not going to be this accurate. We're not spending tens of thousands of dollars on a hyper accurate scope. There are a few organizations in the world that can afford that kind of thing. We're not one of them. I'm not going to pretend we are. There are even fewer organizations that have like really good atmospheric controlled test facilities. We're definitely not one of those. CERN has one, and we're trying to work with them to schedule access to it. So with a PPS, there's a lot more overhead. And so if we were showing a PPS, what you would see on the scope is really plus or minus about 28 nanoseconds up or down. So roughly a picoseconds. So roughly a 56 picosecond window. So total window. So not as accurate as here, but it's close enough that people can sort of think, yeah, okay, I guess that's probably right. Yeah, I agree. PPS has a lot more overhead. There's definitely going to be a bit of skew from the actual trigger versus the conversion of that trigger from digital to analog, et cetera. So it's a way to show people, that these numbers are accurate. But, again, there are a lot of people on the phone on this call who know this stuff. So everybody knows this is accurate. Now, so this is a great little tool. But then ultimately, this brings us to another problem in the real world. So we have an FPGA device. Typically, of course, how do we program an FPGA? We use some sort of programming cable, JTAG, USB, blaster, blah, 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 right? So in the real world, how do you deploy that in the thousands, right? It's not a normal NIC, right? A normal NIC, you just go to the PCI slot, plug it in, put the cover back on the server, push it back into the rack, connect the network cables, you're done, over, right? But an FPGA platform, you've got to look for USB headers inside the server. Not every server does that. So then you're trying to string a programming cable, somehow out of a back slot. Maybe, you take a PCIe bracket, or you're sort of jamming the cable into a little crack, in the panels to try to get it to then plug in to a USB slot on the back panel. That's not scalable. So if you want to deploy these things in thousands, that can't be. If you want to monitor, you want to be able to monitor without the need of a programming cable. If you want to update the logic on the board, again, in the real world, in production, in a data center, you can't use a programming cable. And so one of the things that we're really proud of is that we've worked to eliminate the need for, in this case, bitware, a software development kit, and a programming cable. And this is exclusive to Ubernic. So if you buy, one of our products uses the bitware 440i. If you buy a 440i directly from Bitware and you put your own logic on it, you need the SDK, you need the programming cable to program it, to monitor it, to do anything. If you buy that same board and you install all of the Ubernic logic, no programming cable, no SDK. And so the next example is this window that I'm highlighting. That's also a White Rabbit monitor. It theoretically could have all of the same information that's in the human readable White Rabbit monitor. I've clipped it down so that it doesn't, run so long, and we can make the terminal window a little bit narrower. But if you look at this third field from the right, that's offset from master. And so now we've created something that is deployable at scale. And we've created a monitoring tool that through simple redirect can deliver these values to a database with a SQL call or to a flat file, or other mechanisms that people use to build monitoring for their environments. And we believe that this is key to move some of these capabilities from small volume niche to mass consumable common deployment. So human readable is cool. As humans, we can look at this and say, yeah, it makes total sense. You can stare at it, you can look at the different fields and wonder what they are. But at the end of the day, in a real data center, multiple data centers in a region, data centers, mass global deployment, human readable monitoring is useless. And so machine readable, machine consumable monitoring is the key for mass deployment. So again, this window that I'm circling, that's the White Rabbit monitor as machine readable. That's something we did. It's not something CERN did. Next, this window here, this is PTM. And PTM is using the timestamps that are going into Ubernic from White Rabbit. So these are picosecond timestamps, picosecond time. We have picosecond timestamps in hardware. So if we timestamp a frame in hardware, that's a picosecond timestamp. And our PCAPs have picosecond time. And so in terms of PTM, we start with picoseconds, but unfortunately, of course, as we know, the server doesn't understand anything other than a nanosecond. So we're truncating to get to the nanosecond. And so this is PTM ticking away. You can see the comparison at any individual update in the column that I'm highlighting between the host real-time clock and the Ubernic clock with each update. And the last piece, Ahmad, you want to describe this one?
Which one?
The top window here on the left, to give
Oh
me a
yeah,
moment to take
yeah.
a sip of water.
So this is the correction. Basically, the timestamps, they come within a certain granularity, and then if you add this value, but I don't remember what like the units of it. It was like in picoseconds or something, right, Seth?
This one is nano, and
Yeah,
then it's the offset from where the PPS the should have been generated
yeah,
versus when it was actually generated.
yeah, yeah. So basically, if you add this, you get like I think you go down to 2 nanoseconds or something to that granularity that we have in that list, 4 or 2, depending.
So we're 2 for PTM. We're a 2 nanosecond device for PTM. And the top window, of course, is the TGPIO, the pulse per second being generated.
That's right.
Um, so the windows on the left are, again, that comprehensive front to back precision time capability. And then continuing, but now moving away from that, the bottom right, this is clearly, again, machine readable ticking. These are now the actual board KPIs. So of course, there's a timestamp. We've got the FPGA temperatures right here. So 82.6 degrees centigrade. This is updating once a second. So it's a variety of KPIs, both temps, wattage, volts, etc. But again, machine readable. And again, this is the key thing. How do we take products and genuinely commercialize them? When we talk about precision time, we're talking about, again, generally very special purpose, very niche in terms of the overall, the massive amount of global computing equipment and data center equipment, et cetera. And as we know, what does CERN want to do? CERN has their collaboration partnerships because they're trying to take technology that was created there and commercialize it and push it out to the real world. And so again, I hate to bang on about this, but we're really proud of it. Removing the programming cable, removing the SDK, and making an FPGA board as plug and play as any normal ASIC-based NIC removes massive barriers to adoption. So we can monitor White Rabbit in machine readable form. We can monitor the board in machine readable form. And while I don't have this in a window, I said we can even program the FPGA without the SDK. So we have an application that we built. We can program the FPGA across the PCI bus. That sounds pretty cool, but we've even taken that a further step. So under normal circumstances, when you're programming an FPGA board, you're putting logic into the flash memory on that FPGA board. And you, of course, can manually work to move that logic into the FPGA chip. But you've got to be a reasonably competent developer to do that. And again, in the real world, that's not going to be happening. So under normal circumstances, people will power cycle the server. And as the power is withdrawn and then the power comes back to the PCI slot, the logic that's in the flash memory is moved to the FPGA, and that's how you update a board in production. But in the real world, you can't just power down a server whenever you want. These things are used 24/7. In financial services, they're used, what we say 24 5/5, Monday through Friday, and you get some maintenance windows on a weekend. But if you need to do something when you need to do it, you don't want to wait for the weekend. So we've actually created the ability. So as we update the flash, we then power cycle the PCI slot. So we effectively bounce the PCI slot. We take advantage of the fact that PCIe allows hot pluggability. We then withdraw power from the PCI slot and only that PCI slot. We then return the power. The board, of course, says, oh, okay, I'm coming to life. And it takes the logic that's in the flash memory, puts it on the FPGA chip. And so in really about 2.5 minutes, with only impacting that single PCIe slot, the logic can be updated. The rest of the server continues to run uninterrupted, no issues, no other PCIe slots are affected. So again, mass adoption depends on these kinds of things, right? It's not just about the capability of White Rabbit or the capability of PTM. It's figuring out how to make this stuff really usable in the field. So that becomes the holistic of the product. And then we come back to where we started, Network I/O. And so we have a little test application that we call Taser, testing and simulation rig. That's also an FPGA-based tool. So what you can't see is that there are actually two FPGA boards plugged into the server. One is running UberNIC, one is running Taser. And so what I'm going to do right now is do a quick Taser test. We're going to send 50,000 frames from Taser to UberNIC. The frames are going to be received in UberNIC. Network headers are going to be processed by the stack in the FPGA. The payload will be transmitted across the PCI bus to the host. What we call a tick-to-trade application will then receive that message, immediately transmit it back across the PCI bus into the FPGA. We build the network headers, we build the frame, we transmit it out, and we're snapping the timestamps again on the external side of the QSFPs. And you'll be able to see what this looks like. I'm going to run it twice. It's obviously been sitting for a little bit of time, so I would expect the max latency in the run that I'm about to do to be slightly on the high side, and then we'll run it again, and we can expect it to be slightly lower. So again, if you've ever tested stuff and maybe you've seen things go at line rate, but you'll be amazed to see just how quickly this happens. So there's the actual test, and then there will be some number of seconds while we actually take the data off of the FPGA board, move it across the PCI bus where we further process it. So I'm going to run that. You can see the details of the run. So 50,000 frames transmitted on the left where it says NB packets, 50,000 on the right. The first is just an ARP message. So as you saw with your eyes, it was almost instantaneous, 50,001 sent, 50,001 received. And the performance results are here. So total iterations, 50,000. We begin with a count of 0. So index is 49,999. So all frames were successfully processed. The minimum latency was 823 nanoseconds. Maximum was 5,386 or 5.3 microseconds. Max latency. So I'm going to show you a slide in a second. We're like the only vendor in the world that runs around talking about our max latency. So our max latency is actually better than most network stacks' minimum latency. 80th percentile, 900 nanoseconds, 90th, 912, 95th, 922. You can see that. I'm going to run it really quickly one more time now that it's warmed up a little bit, see if we don't get slightly better performance. And now you can see, previously ARP was done. And so this time it wasn't necessary. So we get slightly better. Try it one more time. And then just for shits and giggles, let's change the number of messages. So instead of 50,000, how many shall we do? Anybody want to volunteer a number? Okay, everybody's being shy. Dan, what do you want? I'm going to pick on you. How many frames?
So I think David just put 50 million.
I can't do 50 million. That will exceed the size of the memory on the board.
Yeah.
And even at 10G, that's going to take a little bit of time.
Right. So could you do 1 million or that's still too
Sure.
high?
No, we can do it. Let's do 1,250,000.
Okay.
And let's just make this a little bit smaller. And we're doing this at about 8.5 gigabits per second. So the rate delay is the spacing between frames. And so we're setting a clock cycle delay of 56 clock cycles. Each clock cycle is 3.1 nanoseconds. So, again, in terms of overall line rate, this is roughly 8.5 gigabits per second. So now we run it. There you go, 1.25 million frames. Every frame was successfully processed. And as you can see, the latency is now slightly better in terms of min and 80th, 90th, and 95th. Max slightly higher, but of course we're going across the PCI bus to the host. So, at the end, there's still software involved, but that was 1.25 million frames at 8.5-ish gigabits per second. Min latency 786, 95th percentile latency 888, 16-byte frames. So as everybody knows, smaller frames are theoretically more difficult to process. Sorry, somebody started to say something. I guess
No, I was just saying good.
Yeah. So that's Ubernick as a Nick. And then I'm just going to go to the full deck for a brief moment and come back to precision time. This is older, but this is a chart of the skew of the Ubernick PPS to the White Rabbit Switch PPS. This is what I was mentioning earlier. So when we look at it from a PPS standpoint, it's sort of 95th, 99th percentile, about 28 picoseconds up or down. And then PTM. And this is a way of looking at just how accurate PTM is. The data here, or the charts here, this is something that started, when did we start putting this together? So it was me, Kevin Stanton, and then Dave Zage, and then of course Kevin left. And ultimately, with a slightly different coloration, Dave showed these charts at OCP in October of 23. And so this is showing exactly what you see. The top chart is a scatter chart of the time resolution of the host real time, or the delta between the host real time clock and Ubernick on the PTM updates. And so, as you see, 95th percentile is plus or minus 4 nanoseconds, and 99th percentile is slightly broader. It's plus or minus 6 nanoseconds. And then the bottom is an overall distribution at different CPU loads, ultimately showing that pretty much regardless of CPU load, PTM is still extremely consistent. So unlike PTP4L, ultimately PTM is pretty much CPU load induced, not susceptible to CPU load induced degradation. I think that's it. I came in under an hour. That's pretty good for me.
Yeah.
Any questions? Yeah, thank you. You know I can talk. Any questions?
Seth, I have a question.
Sure.
When you do the scope
Kevin, you're
measurements,
there. Hey, sorry. Yes, when we do the scope measurements.
what do you do about the cable lengths, and what do you do about the time base in the scope?
So cable lengths, we work very hard to make sure they're equal. We get into a little bit of challenge with the dongles. So we try to get 25 centimeter or shorter dongles to actually connect to both Ubernic and the White Rabbit switch. Ubernic has WFL IPEX plugs, so they're pretty damn small. And the White Rabbit switch has, or at least the switch we use has SMC. So we try to get really short cables there, and then we have, at that point, SMA connections to the main cable, and then BNC on the other end of the cable to the oscilloscope. The scope that we have, honestly, who was it? I think it was one of the CERN folks who said about our scope at ISPCS last year, wow, that's pretty good for $400. It's 200 megahertz. It does the job that we need it to do. We do have a Time Tagger Ultra from Swabian, but we don't carry that around. And of course, it doesn't have its own scope, so we've got to display that on a computer monitor, et cetera. I wish we were Meta or CERN or some other organization like that that could afford a really, really, really good scope, but we're not in that position at this point. But obviously, the higher the capability in terms of acquisition, data sampling, et cetera, the better particularly the calibration, because we need the scope to calibrate White Rabbit. And so the more granular we can be, the better the calibration will be. And again, if we can take all that into an environmentally controlled room, so much the better, right? Because when we're talking about picoseconds, I mean, like we're literally talking about like teeny tiny fractions of a trace. And now, every little thing matters. If there's a temperature difference, a humidity difference. Manfred's actually, for those of you who don't know Manfred, he's one of our engineers. He focuses on precision time. I was actually he's based in Japan. I was back in the Japan office for March and part of April. And he's working on, with the oven control oscillator, we're working on some holdover logic to provide better capability for trading firms. So right now, a trading firm will either see time as synced or not synced, and if it's not synced, then they change their behavior. As we know, we can lose sync to a grandmaster, but with the right oscillator, we can still have perfectly valid time for a pretty long period of time in some cases. So we're working on that. And at one point, I opened the door of the office, and the balcony door was already open, and it's just like a long alley. And I opened the front door, and a burst of wind blew through and blew past the board. We don't work with closed servers. We just have open skeleton chassis. And Manfred literally said, whoa, because on the scope, the line jumped when the air blew across the FPGA. That's how fine-tuned, these level, or not this level you're looking at right now, but when we're working with White Rabbit and we're talking about single-digit picoseconds, it's that sensitive.
Okay, thanks.
Hey, Seth. Always
Hey,
great to
Kevin.
see you.
You too. I'm glad I
Great,
called you out. I didn't even realize you were there.
great work and inspiring as usual. I love this last diagram. Actually, it's really, really beautiful. Question, Seth. I noticed that while you were running live, and kudos to you for the guts to do live demos in public. I noticed there was this clock frequency change unexpectedly. Any idea? Was that intentional or?
In PTM?
PHC to sys, the second to top box on the left.
Yeah,
Just now and then there's a little.
You noticed it. I didn't. God only knows.
Okay, all right.
It's sitting back in the office. We don't have an air conditioner. I'm sure it's 9 o'clock at night here. I'm sure it's reasonably hot. So, there could have,
Okay.
and there's a lot of test equipment in that area. So
Yeah.
that little corner of our office does get hot.
Yeah, always great to see your work. Thanks.
No, thank you. Other questions? Oh, actually, wait. So, Kevin, let's just come back a second. So, reality is this slide, these charts, right? These began with you. And Dave just carried it forward with me from where you pointed us.
Yeah, it's really nice to see the data. Yeah.
So,
And by the way, 1 nanosecond, I guess I can take the blame for that. I didn't imagine that there would be any interest in going below a nanosecond, but certainly if you're going from device to device with the PCIe root port as the common clock, yeah. So maybe there's some work to be done there in the future.
definitely. And I think I don't think Julian's on, but that this is a great plug for Julian and something he came up with called PFM, or precision frequency measurement. Ahmad can talk in more detail about that, of course, in Julian's absence. But yeah, there's a strong desire, I think, from a lot of people to continue to push this forward and work to really get below the nanosecond. Obviously, from the White Rabbit standpoint, to be considered genuine, White Rabbit, and part of what's going on in the White Rabbit community is we're working with the UNH Interoperability Lab to come up with actual qualification testing.
Right.
And there'll be different grades of White Rabbit, but to be able to say you're White Rabbit, you're officially White Rabbit, you have to demonstrate that you can do time resolution below a nanosecond. Not once out of 50,000 measurements, but at a high percentile basis.
Yeah, man, I saw that you joined the leadership of the cooperative to
Yep.
make that happen. That's great.
Yep. Any other questions from folks?
Have you tried with any non-Intel CPUs, PTM?
We have tried with the AMD WMX, WM, WX, I forget the exact name or exact family number. So they say they're PTM capable. Maybe they are, maybe they aren't. It definitely does not work with PTM out of the box. So we plugged our card in. Obviously, PTM works for us on Intel CPUs, but it did not work on that CPU. We have also implemented CXL. That CPU also claims to support CXL.
Did AMD tell you that?
It's in the BIOS, actually. We were surprised. We got a couple of these CPUs.
That is a BIOS AMI?
Yes.
That's shocking.
I'll send you the details when tomorrow's a holiday. I'll send you screenshots.
I cannot say a lot of things, but unless it's like I don't know. I'm not saying
it didn't work. So
okay, great. Yes.
I'll send you pictures.
That's definitely a bug. It should not show.
I'll send you pictures of the BIOS. The BIOS also says it supports CXL. That didn't work either. So
that's a wild card BIOS,
God only knows. So we didn't really try to mess with it because we weren't trying. There's only so much we can do. We have actually, with due apologies to Intel folks right now, we have actually worked really closely with AMD on the Turin CPUs, the latest generation EPYC. And they've implemented something called Smart Data Cache Injection, or SDCI. So that allows us to direct data from the FPGA to particular CPU cores. And even though they own SolarFlare, they actually came to us to ask us to work with them. So we implemented it, tested it, and AMD is running around like talking about SDCI using our slides of performance. Theoretically, that CPU also supports PTM and CXL, but we haven't even tried on that yet.
Question for you, Seth.
Yep.
If you find the opportunity to move all your IP to ASIC, would you benefit in terms of performance? In terms of performance.
Didn't you and I have a heated debate about ASIC versus FPGA a few months ago?
I'm not surprised.
Would we? I don't know that our code base would ever be so mature that we could
No, no, let's
actually.
say that's mature, everything and so on, and you hit like, your limits of improvement. Would you take the next step? Or let's say, like basically all I'm trying to find is, would an ASIC upgrade, if not now, at some point, benefit your performance? And if so, basically I'm just trying to see if an investor's
Yeah, I mean,
investment opportunity is there or not. That's all.
it's difficult to say. So would an ASIC improve our latency? Obviously it would. There's no question about that. We're already line rate, so that's not, we're not going to magically be better than line rate, but it would certainly improve from a network IO standpoint. It would improve the latency. It would remove the ability to be a programmable smart NIC. So maybe there's a different Uber NIC that's ASIC based that has, the absolute end all and be all of low latency, precision, time accuracy, et cetera. But obviously we would be giving something up from the standpoint of not programmable. So
Have to
yeah,
give up
I think
flexibility.
I think the answer is yes. We would get better latency. We're not going to get better throughput because we're already at the max of that. So, just it would be ultimately it becomes an economic decision. Is the gain in latency going to at least equal the expense of the implementation in terms of increased sales? And of course, ideally, we would want to see multiples of sales versus investment. But it's difficult to imagine how many years it would take to get to a code base that was so stable we could do that. So a good example is, as I said, we support 8 fiber pairs. For each fiber pair, we actually support 128 UDP and 32 TCP sessions. All can run concurrently, and that's and then we can do that for each fiber across all 8 fibers. So we can have 1024 and 250 UDP and 256 TCP across the entirety of the board, all running concurrently with each fiber operating at full line rate. And we can have all of those sessions. So that's great. We thought that's wonderful. And then we talked to a client in Chicago who's like, I want fewer fibers and more sessions per fiber. And we're like, but why? Then you have concurrency issues. Yes, I understand that, but the way the data comes from the exchange. So we're now trimming down the fibers from 8 to 4 and bouncing up UDP sessions from 128 per fiber to 512 per fiber. So the challenge is, we've got clients who have their individual requirements. So an FPGA can deal with that, an ASIC can't. But again, if there's a market and the code base is stable enough, yeah, why wouldn't we?
No, I mean, another reason why I'm mentioning this is because I mean, this is a trend more like, let's say, for the datacom to move toward PIC, photonic integrated circuits.
Correct.
And like basically moving away from all those QSFP and converting this to that and so on. You try to basically have everything co-packaged and just fly with that. But then I don't know. I mean, how much the benefits? That's more a question for David. I don't know if David's still here. Like that's more a question for David. Like how can you take advantage of that? Like I don't know, to process things faster to get more like edge or something. Like I don't know. Like and then for that, I will not see an FPGA sitting beside a PIC. I will see an ASIC sitting beside a PIC.
Well, so interestingly, I was at ISC in Hamburg last week, and there were a couple of photonic networking companies. One that's built, actually two that were doing switches, and one of them is actually reasonably close in Munich. So we're going to try to hook up and test together. The benefit of a photonic switch is, of course, it can just plug into the existing environment, and everybody can continue with whatever devices they're using. So I see that as really, really good. There are companies like Oriole Networks. I forget the name. There's a US company in Massachusetts that's doing photonic, but they're all focused on, like 800 gigabit, 1.6 terabit per second backbones, not, the in and out of enterprise servers. And ultimately that's where the world is going. But I think, the technology has to be perfected. Obviously, the primary backbones of the environment need to be upgraded for any of this to make sense. This isn't going to start because an enterprise server plugs in a photonic NIC. It's going to start because the other components of the environment have already converted to photonic, and then that last little bit, as Kevin likes to say, the last centimeter, so to speak, then that can convert because the rest of the world has converted. Anyway, that's my opinion, but there are far more smarter people than me that are opining on it. David L. from Chicago. Yeah, Ahmad was talking about a different David.
No, I was talking with David L.
Oh, you were? Oh, I'm sorry. I
Yeah.
apologize. Then David L., please speak up. And actually, David, it was good to see you in Chicago a couple weeks ago.
Maybe David doesn't have access to microphone or something.
Yes. He sent a message in chat, though. He wasn't sure if you were directing it to him.
Yeah, no, that was David. I don't know another David that does this.
Okay. So David seems to be unmuted now. Yes, we can hear you.
Yeah.
Yes.
Hey, perfect. No, I was just saying, in terms of the ASIC, I would expect on the power side, it would help. The problem we tend to run into in this space is actually the PCI Express controller of the CPUs itself. And so even if we make the NIC dramatically faster, if we're plugging into something that is hundreds of nanos, it sort of kills the point. Even if we go from a moderately expensive FPGA to one of the bleeding edge ones with 2.6 nanosecond SerDes. But if we could fix that, it could be very interesting. I'd be extremely excited for things like this. So you start looking at CXL, and imagine you have a sea of DIMMs, a sea of NVMe, a sea of GPUs. Instead of trying to use something like CXL interface with sort of the core of the city with a cut down protocol, that could be very powerful. And that's where it gets very, very exciting in the future, is that we basically break up the motherboard and just have a sea of devices all connected over some sort of simple networking protocol.
Absolutely.
And then
David, I now see your comment about duct tape. So you can see me smiling.
yeah, you were describing exactly what I once did at one of the major
David,
data centers.
This tells me this I mean seems to me that, like, let's say that SmartNIC approach is perhaps the best, because you can perhaps, if you can offload all that what is supposed to run on layer 7 straight on the SmartNIC, you react super fast there, and then you get from the CPU, let's say, the information that can wait, or
100%.
Oh,
and that's exactly what most of the HFT firms do. And there's all these different APIs for essentially preloading responses. And you just say, find a particular packet where this byte has this value, or less than or equal to, and then here's a series of Ethernet frames.
Yeah, and then release an already queued up order.
Exactly.
And then
so
of
that
course
kills the ASIC. Yeah.
Yeah, and then
the ASIC is still useful for power, though, and
power. Who cares? I mean, you're making millions.
No. For trading, it's a different story. But I'm thinking more like a CXL model. If I have an AI data center and I just have absurd amounts of gates in different forms that I want to connect them, then it starts to matter a lot more.
Interesting.
And and another thing with all of this, trying to stay away from the host side, we do PCIe or CXL bridges or switches internally in a server between an UberNIC as high performance network IO and a GPU. So NVIDIA, of course, just open sourced NVLink. So now we can theoretically go directly to the GPU without the need to actually involve the CPU itself. So we sort of keep everything on the network side of the PCI bus, so to speak.
Cool.
Yep.
Another one, Seth, I don't know if we talked about this in Chicago, so apologies if this is duplicate, but one of the ideas I've always pondered is trying to instantiate a soft core CPU inside the FPGA and then running Linux on that as basically a way to cut out the PCI Express bus. Is that something? What are your thoughts on that? Obviously the clock speed will be lower, but
yeah, I mean, certainly that's been done for a number of applications, to try to get non-hardware developers to be able to put logic, on an FPGA in air quotes.
Exactly.
So Intel/Altera, Intel PSG at the time, for their CXL engine is actually a soft core. Not that they will tell you that. And, for a number of reasons, that being one of the primary ones, the now Altera CXL IP, while being 5 to 7% lower latency. We've implemented CXL Type 3 in an unconventional, not memory sharing at memory pooling, memory aggregation, but just to get lower latency across the PCI bus. So we do CXL Type 3.io from FPGA to host, and then we do .mem from host back to FPGA, and just that one leg, which is roughly 22% lower latency than PCIe, ultimately is responsible for an entire network I/O run, where the entirety is 5 to 7% lower latency. So that one leg is responsible for a lot, and that's with ultimately it works. They were able to get it to work. They were able to get it to work with a significant amount of effort. But if they had not done it with the soft processor and they had to really do it in RTL, it would have taken them a lot longer. Now, one of the other downsides of it is that the overall logic element usage. So the Altera hard IP for PCIe 5 is about 15,000 logic elements, give or take a few. For CXL, 156,000.
Whoa.
That's the soft processor.
I'm surprised it's that big, actually, unless it's all raw just for caching.
Yeah, we were too. When we were like, whoa, wait, what is this?
Yeah. Did you pull it open with the Explorer by any chance to look at the floor plan to see how much of it was RAM versus the actual logic elements? Or
I did not. That would be. I'm not an RTL engineer, so I'd have to go back and ask the engineers if anybody ever did that. I was satisfied with the holy shit. Why is it 10 times larger?
I'm surprised it's that big. I mean, it's been a while since I looked at the spec sheets from Altera on the size of their soft cores, but that's big.
Yeah, we. I mean, it really is actually. So, we're using the AGI 023, which is, and we also use the 019. They're pinout compatible. The 019 obviously has fewer logic elements, and we were using the 023, and the idea was that we would use the 023 would be for the SmartNIC because it had more elements on it. And then we started looking at CXL, and we're like, dear God, we can't deploy this on the 019. This with our logic would consume like 75% of the chip on the 019. We're looking at it at again, then Intel, and we're, guys, 15,000 for PCIe, 156,000 for CXL. Can you explain that? And everybody's like looking at their shoes.
Yeah. No, I remember seeing similar things like a decade ago when we were using their Mac from Altera. Our compile times would be like 2 to 4 hours, and we wrote our own simple one, and we got it down to 5 minutes. I mean, just dramatically different logic utilization. If you can throw everything out, you don't need.
Indeed.
Seth, like this was I mean, it's such a shame I didn't notice it happened last month that they opened NVLink for basically all kinds of.
You checked after I mentioned it, I see.
Yeah, I mean, I didn't
You were
know
like
that
immediately Googling.
No, because I mean, now I can probably talk about it. I was trying to sniff it and try to open it, but it was like too complex. I mean, 2 years ago, and I mean, this really opens up so many opportunities. Are you making I mean, you don't have to answer this because like
of course we're gonna implement. Of course.
Awesome. Yeah, I look forward for that because I was really looking for like putting heterogeneous stuff on NVLink rather than be stuck with whatever they have. I'm quite surprised like NVIDIA is doing this.
I guess they're trying to, head
Be
things
nice.
off at the, yeah. Well, no, I was going to be nice. Obviously there are large parts of the environment that don't like, the closed nature of everything NVIDIA does. So I see this as an effort by NVIDIA to cut off at the pass, so to speak, efforts to create more open capabilities. So if NVLink is open, that's going to kill a lot of other efforts to build some sort of more open source competing
That will
something.
probably kill CXL. Like, I don't know.
CXL, I mean, that's a totally different discussion topic.
I mean, for this, for
how
the
many
AI
Intel?
stuff.
How many? What do we have? So we don't have anybody else from Intel on. Okay. I mean, really, for reasons we all understand, CXL just is, yet another example in a long laundry list of examples from Intel of technology that's been created that they've spent God knows how many tens of millions of dollars on, and then they failed at the last foot. So, you've heard me whinge about lack of ecosystem enablement and that it fell to us to work with all of those different OEM vendors on testing, including working with AMI on, their CXL capabilities, and then working with all of those different OEM vendors on testing their BIOSes, et cetera. I mean, we had to do that. Who the hell are we? Intel didn't do it. PSG, Altera didn't do it. And so you wonder why CXL didn't get any traction, right? I mean, if the company that brought it to market isn't out there screaming at it, the top of its lungs, so to speak, CXL,
Yeah.
is it any wonder it didn't get much adoption?
Yeah, I have to wonder though, did they really want it to get adopted, or somewhere like you said, you put out there that you're going to do it so that other people don't, but then you drag your heels intentionally for as long as possible, because that could have a dramatic impact on their margins if you suddenly don't need that many Xeons to hit petabytes of RAM, for example, or accelerators.
Yeah, so I don't know if this is true, but I know what we were told. And, we do work really closely with Intel. We were told that the Xeon 4th Gen wasn't really, so CXL goes live in that. But the view was that wasn't the CXL that they wanted to push. And even in the 5th Gen Xeons, that they didn't want to push it because that was still CXL 1.1. So what we were told was that was an initial implementation, get it into silicon, find any kinks, and then optimize it for CXL 2.0 in Xeon 6. We're at Xeon 6 now, but it's a completely different Intel world. The reality today is different. The people are different, right? The people who came up with the strategy 5 years ago are like, I don't know, sitting on a beach, sitting at home playing PlayStation, hanging out with their grandkids, whatever it is they're doing. What?
PlayStation.
Okay. I like, who are you pointing to, right? Neither you nor your wife are like hanging out with grandkids. Is your mother-in-law floating around?
Yes.
Okay, there we go. Yeah, it's good that she's there, actually. So yeah, and here we are at Xeon 6, and nobody's talking about CXL. So somebody was asking me, can we do Ultra Ethernet? And I'm like, of course we can. Well, are you going to? No, we've been burned once with CXL. We're taking a wait and see attitude about Ultra Ethernet.
I literally just pulled up their press release and was about to paste it to the chat and ask you about it. It was 1 week ago today. I'll paste it for the sake of record anyway, because it's already on my clipboard. But
Gotcha. See, somehow I'm like, half a picosecond ahead of you right now.
Yep, you're preemptively sending. Another trick we use.
Yeah, exactly. Actually, wait, what is that called? There's a lawsuit going on now in Germany.
Yep, optimistic
Mosaic.
messaging.
Yeah,
others.
exactly.
Yeah.
Something like that. Mosaic is suing and then saying that the local regulator is incompetent. Well, I mean, they're not really a local. I mean, I guess technically they're a local. It's like, I mean, that's as local regulator as you can possibly get. So
They needed to find someone who they thought maybe had jurisdiction. So I think they tried someone else first, and they got rejected. I forget the details. But
yeah, and then the second one got rejected. Anyway.
Yep.
That's a different long conversation. So if anybody wants to understand all the tricks of low latency trading, David and I can bore you all to death for quite an extensive period of time. With
Read
all
my
sorts
patent. It covers like 30 of them, even overclocking Ethernet.
Yeah, no, actually we do that with our transceivers. So we run them at 20G.
There you go.
So every teeny tiny little corner that you can cut, you would do.
Yep.
If it's at all possible. Any other questions from anybody?
Covered most of them.
Cool. Sorry, last thing, just while I've got David. So David, we were talking about, I guess it's summer now, but I'd still love to figure out how to do something for one of your groups when you think that's relevant.
Would love to. I just got back from 3 weeks of traveling for conferences, but I have a lot of cool gear. I just got one of the I forget the model number for it, but the Xilinx FPGA with the 2.6 nanosecond transceivers. So I'm
Oh,
really curious to set that one up. The XL something. I
yeah,
could pull it
it's
quickly.
what is it? Well, there are two, right? There's the bigger
It's
3524.
the older one. Exactly.
Yeah, so
Um,
they gave us a couple of those, and I'm like, I don't know what we're gonna do with it, but thank you.
Yep. 20 nanoseconds faster. Hey.
Well, that's the problem with it, right? It's now so fast that people really can't build effective strategies to take
Yeah.
advantage of it.
We've basically gone to the point now where the strategy is not to rewrite your code, it's to order more fiber optic cables and play the lottery. Unfortunately, that's the problem. I mean, it's
Or less fiber optic, right?
we wish. No, it's absurd. Like I remember one of the exchanges, actually, this is in public domain, Eurex, that is one of the two major ones where like every picosecond counts. They had to pass a rule that no customer can buy more than I think it was 32 fibers. And these things run tens of grand a month. So that gives you an idea of just a single exchange, how much some are willing to pay for connectivity, because that's where the alpha is now. It's not fighting, a nanosecond on the RTL, unfortunately.
And so what you're doing is basically replicating the exact same order across all those different fibers, knowing
Exactly.
that one of them will make it to the order book faster than the others. And so, why there's an order type called IOC, immediate or cancel. So you
Yep.
send all these things as IOC. Sorry, there's a really bad, not safe for work analogy that's in my brain right now. I think I've said enough for you guys.
I was about to say it.
So one makes it, and it results in a trade, and all the others die.
Yep. And another way you can do that, in addition to the IOC, is you can, I think, depending on the exchange, you can even send the exact same Ethernet frame in some cases, and then that way any one of them is going to plug the hole essentially in the TCP buffer, and then go in, and the rest gets silently discarded by the stack. But it's a concern because then it overrides the engine, and it also screws up. I mean, to the point of this call, like timing. If you're trying to figure out, well, the next message that did get in, when was that sent? And you have all these IOCs, you never see it in the market data. So you don't actually know that gap was there, and that you actually would have had to be even faster than it appears based on the historical record. That's always been my pet peeve. The exchanges don't disseminate that.
Exactly. So for everybody else, an IOC, because if it doesn't result in a trade, it's canceled, and it never makes it into the order book. Therefore, it never makes it onto the outbound market data feed. So you know that there are all of these messages that are hitting the exchange. I mean, you know that, but you don't see them on the market data feeds. So you don't really know all of the messages that are actually hitting the exchange infrastructure.
And therefore, you can't know how fast you need to be to have actually gotten the trade. And so it screws up all your back testing. And it's not just those doing the speed race. I mean, sometimes you can get so much queuing. You're talking about tens of microseconds or more because of this massive flood of orders that everyone's sending.
Indeed.
But another instance of where having proper, accurate timing and complete data is very important.
Yes. We lost Ahmad, I think. Did we?
No?
We did.
Nope, you still
you're
on.
there.
Someone
Okay,
dropped
cool.
off, but
all right, guys, look, it's 9:30 at night, my time. I need to eat some dinner. I
Right.
appreciate the opportunity to talk to everybody, and Dave separately pinged me, of course.
100%.
And then I think collectively, Ahmad, is today going to be the day, or is it going to be tomorrow?
Not today.
Not today.
Are we awaiting an announcement?
No, it's just
Oh, okay. It's all good.
all right.
Send me a note.
Yes.
Always a
Right.
pleasure,
All right, guys.
everyone.
Yeah,
Right.
everybody have a good rest of the day.
Yes.
Looking forward to talking to you next time.
Yes.
Same.
Bye,
Take care,
everyone.
everybody.
Cheers, everybody.
Take care.